Hello, and welcome back to Beyond Networks, the evolution of living systems. Last time, we were looking into a type of evolution that is radically open-ended, open evolution. So in this lecture, I want to argue that this type of evolution requires us to look at the evolution of the organism. It requires the organism to be the thing that is evolving. And not just the organism, but also the environment it is living in. So we were looking at the sort of open-endedness of evolution through the perspective of these time-variant spaces of possibilities and their radical context dependence. The type of dynamics of open evolution that I was talking about is generated by constraints that are determined by the actual present moment that enables the set of adjacent possible opportunities available to it. So there's a radical and continuous emergence of new enabling constraints. What's going to happen next always depends on the present moment, and the constraints that determine what can happen are generated in that present. This is important for not just an organism that evolves, but an organism that lives. Remember, it's sort of constantly regenerating its own organization. So these continuously emerging enabling constraints entail a constantly changing set of possibilities. What does that mean? Entailment is a logical sort of implication, right? So these enabling constraints are basically new rules that are coming into play at each moment. The rules of the game are rewritten at every moment in time, and therefore the state of possibilities, the configuration space of the system, is also changing at every moment in time. So there is no pre-given box, like in the Newtonian paradigm, where we just define a box, state the rules in that box, set some initial conditions, and we can determine everything that's going to happen in the past or the future, just like the Laplacian demon. You can't do this for the universe as a whole, as Lee Smolin argued, but also not for organisms, especially not evolving organisms. So true novelties consist of newly emerging constraints that weren't there before, new rules that fit into the existing environment and organization of the organism somehow. For something to be a novelty or an innovation, it needs to make sense. And this sort of sense-making is radically context dependent. It depends on the entire state, present state, and the history of the universe so far. So it's radically not predictable. And so in the last part of the lecture, we're going to complicate this situation even more by talking about the co-emergence of the organism and the experienced environment. But let's focus first on this idea that novelties are newly emerging constraints that have to fit radically into their present context. And so these constraints, when I say enabling constraints for the adjacent possible, we can translate that directly into the organizational account of the organism, especially the version that we had from Alvaro Moreno and Mateo Mosio that saw organizational closure of the organism, remember that, as a closure of constraint. Just to briefly remind you how that works, let's say we have a sort of set of constraints here, labeled by C, 1, 2, 3, 4, 5. And some of these constraints are generating other constraints. So you can see here, the arrows represent physicochemical processes, metabolic reactions, for example. They can go from A1 to B1, so you have a bunch of chemicals that are being converted into some sort of product, and there is a constraint indicated by this wiggly arrow here that works on this process, like an enzyme that works in this process. Now, a bunch of these constraints both generate other constraints. So sometimes constraints are made by chemical processes. Enzymes are also produced by catalyzed processes. These constraints influence the process at a different time scale, indicated at this side of the diagram here. Okay, and for a bunch of these constraints, not only do they generate at least one other constraint, but they are also generated at the same time by at least one other constraint. So just like Kant said, this is what makes living systems special. Okay, every important, essential cause that you need for the continued existence of the organism, in this case, every constraint is produced by another constraint and is producing other constraints. So is both end and means at the same time. And this is what makes organisms special. Okay, so novelties can come into this, because for a new constraint to fit into the organization of the organism, all it needs to do is it needs to be generated by and depend on at least one other constraint. Plus, one other very important condition: it must conserve the overall closure of constraints. But as long as you conserve this closure property, you can add and subtract as many constraints as you want. So living systems are highly transient, they change all the time, and they're highly redundant. We'll come back to that when we talk about network evolution. But basically, it is easy for new constraints to come and go here, as long as they conserve the overall closure of the constraints. And James Di Frisco and Matteo Mossio have called this organizational continuity has to be maintained. So you can change as much as you want. You have quite a lot of degrees of freedom as long as you maintain this closure. And so this is how novelties, radical novelties, unpredictable, unprestatable novelties can be incorporated. Since there are many different ways to conserve the overall closure of constraints, organisms are constantly adding, removing constraints through work constraint cycles. Remember, so these constraints are producing energy that is channeled as work into building new constraints. This is how life works. Remember Kaufman's cannon field, bean field, while maintaining organizational continuity. So organization, I say it again, is radically transient. These changes are triggered from within the organism. That's very important, okay? There is an autonomy. So what kind of new constraints come into being are autonomously triggered, specified from within the organism itself. Okay, what kind of changes maintain organizational continuity depends radically on the current organization of the organism. So you need to know the organism, the specific structure of the organization of the organism at any moment to know which sort of constraints fit and which don't. Plus, of course, its interactions with the environment. You see, there's a bunch of constraints that are outside here, and we'll come back to that. And remember, animals, organisms are radically thermodynamically open systems. Okay, so to sort of digest this a bit, just by living, and living is a precondition for evolving, the organism is constantly generating new configurations of itself and therefore of the world and its relation to the environment. It's even building the environment as it goes along, as we'll see in a minute. So there's constant opportunity for true novelty, and novelty in the sense of the emergence of new rules to come into play that have not been there before. So this is a strong sense of emergence, a strong sort of impossibility to predict the future in this case. And in this case, in this sense, evolution is radically open. So let's try and look at this from the sort of maybe from the other side, from Newton's perspective, right? So I was telling you when we were talking about dynamical systems theory, classical Newtonian approach, that we can not only determine what the system does if we know the rules, the boundary conditions, and the initial conditions, but if we vary the initial conditions and also the boundary conditions, the parameters of the system, we can check what it can do, what some of its opportunities for change are, given its current set of rules. So what I'm drawing here is this bifurcation diagram from Alberg's paper that shows you what happens if the parameters of a system, like the boundary conditions, for example, change. Then you get different sort of dynamical regimes. Remember, one species was in this sort of regime A, and another one was here. And the bifurcation boundaries are indicated by lines, and they show you what kind of transitions, what kind of opportunities for change are there for these species. And they're very different for A than for D. D can access all the other letters, while A can only really access B and D. So this is a sort of a fixed space of possibility, okay? This configuration space. If we have this physics in a box model of the system, we can predict what it can do only given the present rules. No rules come into play, okay? So Mael-Monteville, in his paper, calls this this sort of space of possibility, the space of actual possibilities or pre-possibilities. Remember, a pre-possibilities is a possibility where you can specifically pin down the properties of an event ahead of time. But you can sort of predict the space of possibilities. Okay, so he calls those actual possibilities. They, in a way, so in the sense that Stuart Kauffman talks about the adjacent possible already existing at the moment, that's the sort of predictable set of possibilities. But because the rules always change in a way that's not predictable, we can now make this space change over time. I just flip it around here for my own convenience. And so as the constraints of an organism's organization change in unpredictable ways, the space of possibilities changes in a way which is not predictable as well. Therefore, many possible configurations are not even pre-statable. Remember the screwdriver that Stuart Kauffman was talking about. There may be an opportunity for a use of the screwdriver that we haven't yet thought about. Think about the evolution of wings, exaptation. So wings, feathered wings, the feathers were for thermoregulation, the wings were for gliding, and then suddenly, by being there, they created the opportunity for flight. And then selection for flight kicked in. But the opportunity for flight was not there before feathers and these flappy structures were there, probably selected for thermoregulation initially. So the function that was selected for changed. This is called an exaptation or a Darwinian pre-adaptation. Okay, and these are not only not predictable, but they cannot be pre-stated because they're radically context dependent. You have to get there in the history of the universe to realize those opportunities have come into being. So any such configuration is only a virtual possibility or pre-possibility. It is not part of our current configuration space. It is a true novelty in a stronger sense than events that can happen within this actual possibility space would give us the impression. This is why the future is always unpredictable. This is why you always get black swan events that you didn't predict from extrapolating from the past or from doing physics in a box where you have artificially sort of isolated a part of the universe to make it tractable. That's not really a valid approximation in this case. Okay, so virtual possibilities are emergent in a stronger sense than actual possibilities, right? Virtual possibilities are truly unpredictable or even unprestatable in many cases, depending on the continuous radical emergence of new rules, constraints at every moment in time. The activities of the autonomous organism, the very act of living, turn virtual possibilities into actual possibilities because the organism is constantly changing its own rules, not just evolving, but as it lives, okay? And this sort of activity of living is the very foundation that enables the organism to evolve. So the constant emergence of these new rules has been called enablement by Giuseppe Longo and Mael-Monteville in this paper that I indicate below here. So this is an enabling sort of evolution that creates new opportunities. And it is a dialectic process which enables truly open-ended evolution, unpredictable, unprestatable evolution. And you will completely miss this if you only look at the level of genetic evolution, but you also, of course, will completely miss this if you use the Newtonian approach, just like the two theories of innovation that I was showing you in the beginning, epigenetic innovation theory and variational structuralism do. They remain limited to these actual possibilities, but not the virtual possibilities. So they miss those. And it's not quite clear how we can deal with those because we cannot predict them. So if the aim of science is to control and predict, we cannot deal with those. So we need a different kind of science, I would say, instead of trying to explain away this fundamental aspect of the universe. Okay, so if you think this is very complicated and sort of your head is spinning already, right? It's an amazingly different view from the mechanic clockwork universe that we usually have. The whole universe is like an organism that's evolving and living in a way. We'll come back at the very end of the lecture to that sort of view. So, but the situation gets even more complicated when we consider the interaction of the organism with its environment. So traditionally, evolutionary theory is based on two fundamental assumptions. One of them we could call environmental autonomy. And here is Richard Lewontin with a quote that describes what that is. The modern view of adaptation is that the external world sets certain problems that organisms solve, and that evolution by means of natural selection is the mechanism for creating these solutions. The concept of adaptation presupposes a pre-existing world that poses a problem to which an adaptation is the solution. So basically, what the environment kind of puts in our way, the problems it poses to us, is under no way under the influence of the organism itself. It's completely autonomous. The environment does its own thing, and the organism adapts. One-way interaction. The second basic fundamental principle is explanatory externalism. And I'm using the work of Dennis Walsh here from his wonderful book, Organisms, Agency and Evolution, where he defines this externalism as the process that introduces adaptive bias in evolution is distinct from and independent of the process that occur within organisms. I mean, it's related to the point before, but basically, the selective pressures are completely independent of the organism itself. It is because we can differentiate the contribution of the environment that we can see it as the principal cause of adaptive change. Okay, the whole of traditional evolutionary theory is based on this assumption, that the major force of change of adaptation itself comes from the environment outside the organism's control completely. But there is a problem with that, okay? So we saw in the first part of this lecture that the organism itself is creating the opportunity for new novelties, basically by living itself, okay? And now we'll see that the interaction between the environment and the organism is also creating new opportunities in the same kind of way. So let me start this argument with an example. Let's look at two organisms that live in the same physical environment. One of them is a porpoise. Okay, beautiful animals related to dolphins. You can see them swimming here, and they are gliding. Okay, so they're gliding through the water. They're very streamlined. So we have hydrodynamics. It's important here. Very elegant animals swimming through the sea. And now let's look at a paramecium, which also lives in water, and see what it does. So this is a paramecium, lots of little cilia on its skin, and it's sort of moving through the water, which is very, very viscous at its scale. So both of these animals share the same physicochemical environment. Okay, one of them is salt water, the other one is fresh water. Doesn't matter here. It's H2O with the same sort of physical properties. But the experienced environment of each organism is very different. It is determined as much by the properties and capacities of the organism itself as it is by the physical properties of the environment. So these large porpoises, they're gliding through the water, while the paramecium has to sort of screw itself through this very viscous liquid because it's so small. It experiences water in a very different way from the porpoise. Okay? So the experienced environment is neither autonomous nor external to the organism. Its properties, those properties that are salient or important to the organism, depend on the organism itself. Okay, this is a fundamental insight, okay? And this is a huge problem for evolutionary biology. Evolutionary adaptations, therefore, are responses to the experienced environment, not the physical environment of an organism. Okay, so organisms, and that follows logically, are at least partly constituting the conditions in which they themselves evolve. They have something to say through their activities, through their way of living. They already have some sort of power to identify those features of the environment that are important to them. And that comes out, again, of the activity of living. So explanation even of adaptation, not just of novelty. Remember, we said there are two things to explain in evolutionary theory. Adaptation on one hand shouldn't be a problem. Novelty on the other hand is a problem. But even adaptation, the explanation of adaptation intimately involves the organism itself, which is nowhere in the current theory that we have. So let me introduce a bunch more examples before wrapping up, and then we move on. And these are two funnily named ones, commingling and intimacy. That sounds very sort of woolly, but bear with me. These are two concepts that were introduced by philosopher John Hogland in the context of the philosophy of mind. I'm trying desperately to stay away from that usually. It's a very sort of complicated topic, but these concepts are really interesting for us to think about the organism as well. Okay, so in a conventional view of the mind is something completely internal to the agent, right? Something in your, the ghost in a shell, right? In your black box in your head, connected to the environment through very narrow channels of perception and action. And this is like the conventional view of evolution. The organism is very separate and just sort of, there's a one-way channel of the environment determining its selective pressures. Hogland says the contrary of this separation is something I would like to call intimacy of the mind's embodiment and embeddedness in the world. Okay, so there is no separation, basically. That's what this term means. The term intimacy is meant to suggest more than just necessary interrelation or interdependence, but a kind of commingling or integralness of mind, body, and world. That is to undermine their very distinctiveness. So we have to stop thinking about this sort of separated processes, right? They generate each other. They completely depend on each other. So the organism and its environment, just like the constraints and the processes within the organism, not only interact, they're not two independent processes that interact, they completely co-generate, co-emerge, and depend on each other in a much more radical way. And this is commingling. Organisms are also commingled with their conditions of existence. They construct and respond to their experienced environments. There's a back and forth, okay? And the perceived environment of any organism only exists if the organism itself exists. Okay, last bunch of concepts here, very important. These are affordances. They were proposed by James Gibson, also a philosopher, who was busy with perception, visual perception. And so he was sort of trying to figure out what is it that we pick out of the environment, what is important, or the technical term salient to us in the environment. And so he introduced this term of an affordance. The affordances of the environment are what it offers the animal, what it provides or furnishes for good or ill. I mean by it something that refers to both the environment and the animal, commingled. It implies the complementarity of the animal and the environment. For example, affordances can be opportunities for the animal to get food, to get sex, whatever, to be pursued, or impediments to be avoided, danger, being eaten. These are features that the animal will pick out. They're relevant to its life and react to it or act upon it. What an organism's conditions provide or furnish is jointly determined, this is important, by the properties of the setting and the capacity of the organism itself. It's not just an external environment. It depends on the organism itself. The organismal agent selects which features of its experienced environment are important for the pursuit of its goals. So this is called the selection of salient features. This only makes any sort of sense if we accept that organisms are agents, of course. Affordances, therefore, are emergent properties of the commingled organism environment system. So we have the same sort of dialectic dynamic here and in the organism itself. So the sort of rules, the constraints of the organism are emergent properties of the organism's act of living, and affordances are the emergent properties of the organism's act of living in its perceived environment. But the principles beneath are exactly the same. Dennis Walsh calls this situated adaptationism, Situated because it's radically context dependent. An adaptation is a response, not to a niche, an ecological niche or an environment that is out there, but to an affordance, something that is relevant to the organism itself. Adaptive evolution is the process by which the adaptive plasticity of organisms conjointly molds both the organism and its affordances by affecting changes in organismal form, the environment, or both. So we can change the environment. We, as a human species, have changed the environment much more drastically than we have changed ourselves over the last 10,000 years. We'll come back to that when we talk about niche construction. So here is a much more complicated and emergent sort of dynamic happening. Organisms are not optimized survival machines. No, but active agents in their own adaptive evolution. And the kind of theory in evolution that we have right now is completely incapable of dealing with this dynamic or looking at investigating the sort of potential role of the agency of the organism. This is a huge problem. We don't even have the methods. I told you in the first part of the course, we don't even have the mathematical methods. We may not have the concepts yet to think about this type of dynamic, which is radically emergent. Again, co-generation. And we're back, of course, at the distinction between Churchill and Marx that I've actually taken from Dennis's book. So it's not just, we build the buildings and then they shape us, like with Churchill. There is no independent two processes that are sort of causing things in each other reciprocally. There's not just a feedback relation, but there is a dialectical relation of reciprocal constitution. Okay, so these require each other. Impredicativity, all of these processes are impredicative. And as Rosen made the argument, you cannot deal with them with our current mathematical tools. To wrap up, so to get the sort of open-ended evolution that I was talking about last time, you need to look at the organism. True novelty and innovation require the activity of the living organism. You won't get them if you only look at genes. Okay, so we need to focus back on the level of the organism to understand what the openness of evolution is truly about. And this is probably something that's affecting these studies in a discipline called A-life, artificial life, that are trying to produce algorithms that act like living beings. And we haven't succeeded with this at all. It's been a total failure, to be honest, because we're probably misunderstanding some of the basic concepts, and we don't have the computational tools to actually simulate that. Even adaptive evolution, not just innovation, is emerging from the dialectic co-generation of the organism and its perceived environment. Okay, so even normal evolution, let's say, not just innovation. If you want to understand openness, you need to not just reconsider radical evolutionary innovations, new levels that come into being. We'll talk about that in the next module again. But also, you have to reconsider the way we treat adaptation. To fully understand what this really means and how far we are from tackling or understanding these problems, we'll have to step back a little bit. And in the next module, I'm going to show you first 3 established different perspectives on the basic process of adaptive evolution. And then we'll compare that to a fourth new agential perspective to maybe get an insight of what we're missing and where this is going. But it's a very tough problem. So if we want to capture this truly radical openness of evolution and the sort of co-generating dynamics of organisms and their environment, of organisms in their act of living, we need a completely different approach than we have today. Beyond the Newtonian paradigm, beyond mechanism, beyond physics in a box. Thanks for listening, and I hope to see you again next time for module number, is it 10? Bye now.